Hello everyone, my name is Mateus Miranda and I'll present to you today the research entitled Wood Frame Facades Requirements for an Efficient Connection System. As a student of the fifth year of Civil Engineering and Urban Planning Department in the INSA Lyon University, I was supposed to do a research then with Sir Fabien DELHOMME from INSA and GEOMAS lab, teacher and researcher, and with the HILTI France, a partner of INSA, represented by Yannick and also by Alberto Martin and Gaël Le-BLOA. And we started this research with the objective to define the main requirements for a system of connection for the wood frame facades. Then for that, we needed to understand the wood construction itself, wood frame facades, and then enter in the details of their systems of connections. The steps were as follows, with a first stage with more theoretical subjects, with the lecture of publications and a lot of standards to understand the theme. After, we had a second stage with more practical work, with the development of the solutions, with engineering thinking and calculations to validate them. Happily, we could had a site visit to see in the practice the facades, the wood frame facades being installed, and also going to a factory where they are produced uh, from the enterprise Alois, where Sir Pitron welcomed us and was very useful to understand the processes. The research lasts from October 2024 to January 2025, then with 4 months of work. Then, starting with the context, it's important to know why to talk about wood construction. Firstly, we understand that before the Industrial Revolution, we had a supremacy of wood in the materials from the choice of materials for the construction. And then, with the advent of steel and concrete, it changed, and then the use of the wood decreased a lot. But last years, with the environmental subject being inputted to the multi-criteria analysis that is necessary to choose a material for buildings, uh, we started searching other materials because steel and concrete are very pollutant, and wood points out there because it comes from a renewable source. More than structural elements, we have other purposes that wood can be applied for civil construction. For example, building facades that are elements that separate internal and external environment. And in the case of wood frame facade, we have generally as main components their own structure, being by studs and beams, uh, insulant materials. We have rain screen and vapor barriers, and internal and external claddings. And the panels can be fixed to the structure by mainly two ways. Firstly, being hung in the front part of the structure, or being just leaned to the edge of the structures. And it's very important because it implies directly in the way we fix the panels, and the systems of connections of them to the structure are our focus here. Then we started looking for the wood frame facade demands to understand better what they need. Then firstly, we understood the mechanical importance of the panels. They don't have a structural function in the buildings functioning, but they need to transmit all the efforts, all the loadings they have to the structure, and not to their all other equals, only to the structure. And as these loadings consist, for example, by their own self weight, The climate loadings that arrive to the facade and should be transmitted to the structure, seismic events that generate loadings and that should be transmitted too. We have the fire subject with the notion that we should model elements of a building that do not contribute to the spread of fires. It's important to have a structure that is easy to install, easy to maintain, and also easy to dismantle if we think about circular economy, with the necessity of replacing pieces of a building without breaking them when we take them off, to possibilitate the use in the future for other purposes. We have the environmental subject, as we said, that's very important. Then the production and installation of the panels should not be too aggressive to the environment. We have the costs that are always a key factor for building components. Then we know that panels should have a plausible cost to be used. Coming back to the nature, we have the sealing properties that are important to the facade elements, because we should avoid air and water penetrating. Then the facade elements should be airtight and watertight. We have insulation properties also concerning both thermal and acoustics. That is very important to facade elements. And mainly due to these three last items, we see mainly the use of the first type of fixation. Because of that, we generate a continuous facade that is more manageable to the concerning the insulation properties. Because if we had the interruptions as we see in the second type of fixation, it would be harder to manage the bridges that it generates, the thermal and acoustic bridges that it generates. Then we see more commonly the first type, and it is this type that we will consider for the research. To understand all these demands, we needed to read publications, but also we took a look to the Eurocodes, that are the standards with the most of guidelines for buildings in Europe, and also the DTUs, that are the Unified Technical Documents, that are the documents for French guidelines. Then we searched the ways to fix wood panels, wood elements to the structures, and we saw that mainly we have two ways: with or without metal intermediates. And for example, we can fix the wood elements to other wood components in a wooden to wooden connection without using them, but it's harder. We decide, in spite of the development of new techniques and in the industrial part of this, the Eastern Asia, it's far from our industrial reality, mainly in Europe. Then we'll focus in the metal intermediates using that are more seen in the studied cases. And then we searched a commercial solution with the existing systems of connection that can be used to fix wood frame facades and also other types of structures that are similar. Then we analyze it too. It's not the focus here, but in the research, in the report, we show some comparisons between them, comparing them mechanically and geometrically, to analyze how they work and what are their objectives in terms of mechanical things mainly. And this was very interesting to better understand what are the major impacts that a system of connection has in the wood frame facade in general. And talking to professionals, for example, we understood that the cost is not negligible. We have from 5 to 15% of participation in the all budget of the panel due to the system of connection, because it's still expensive. But sadly, we didn't find much data about economic part of the wood frame facade, neither about the systems of connection. Then we will focus in the second major impact that we understood, that are the mechanical part, as we said. That's very important, mainly due the transmission of loads that should be made by the panels, then passing through the systems of connection. Then analyzing it with more detail, firstly setting the loadings that can happen in the facade. We have firstly the self-weight of it that works vertically to the facade. We have the wind that comes perpendicularly, but with other components, as we'll show. We have the imposed loads that simulate furniture being held in the internal part, or also people pushing the structure that generates perpendicular loadings too. We have the thermal expansion that arrives in the both directions of this two-dimensional element that is the panel, and then horizontal and vertical that generates loadings because of the friction that it causes. And I have not least the seismic events that can generate loadings in the three directions. To input these loadings to a panel, we modeled one with real dimensions that a partner gave us. Then it's a panel with 20 square meters, and with the real conditions of the support points. That is, we have 4 support points, and they are all different in terms of blocking the movements, and then with the reactions they have. Firstly, we have the support point A that only blocks the Y displacement, that is, only blocks the movements at depth. We have the B point that blocks both the Y direction and also the X direction. That is, it allows only the Z displacement, the vertical displacement of the panel. We have the point C that it's the strictest that blocks all directions. It's fully blocked, and we have the D that inversely to the B point allows the horizontal displacement parallel to the facade, but blocks the vertical one. Then, better analyzing the loads themselves, we have the self-weight that comes from the material properties with a weight of 50 kilograms per square meters that generates a loading of 0.5 kilonewtons per square meter. That is all held by the top points of the panel that are the C and D. We have the wind that, with the hypothesis that we are in the home department in France, with a building of 15-meter high with a rectangular and regular shape, have the basic wind speed of 24 meters per second. That, with this hypothesis, generate also wind pressure of 0.5 kilonewtons per square meter that acts perpendicularly to the facade, and that has a component in the inverted direction that is lower than the first one. That comes from inside of the building. And we have also a parallel component that is much lower, but exists too. And with this, we can understand that all the support points hold the perpendicular loadings because all of them are fixed to the through the y-axis, as I said. But the parallel one is held by only the right points that are the support points that blocks the parallel displacement of the facade. We have the imposed loads that comes from the Eurocode 1 with the linear distribution as we see here, with a given height that is as they are perpendicular to the facade, they are held all by the support points. We have the thermal expansion that depends on the direction. We have the expansion both directions, X and Z, and for each of them, we have loadings that are generated by the friction of these points. That depends also in the normal effort they have, and because of that, the values are different. And that depends also in the displacement the facade, the element of facade has. We have also the seismic events that, according to the geographical data for the Rhone department here in France, also the components perpendicular and parallel to the facade, the parallel that is held by the right points, and the perpendicular one and the 4 points. I said that we would have loadings in the 3 directions for seismic events, but with this acceleration that's not too high, the Eurocode said us we can consider the vertical component as negligible. Then it was exactly that we did. And then we understood that there are three main mechanical functioning answers that the systems of connections should answer. That are the strength, firstly, to resist to all the loadings shown, the adjustments during the moment of installation, as I'll show, and the expansion gaps that are the possibility of moving of the parts of the panel that should be free to not generate more reactions than we expect. Firstly, about the strength, we have the envelopes that we can make with combinations that are given in the Eurocodes. That is a lot of situations that vary in terms of conditions of happening and coefficients that we consider to search the worst case, that is the most unfavorable case of loadings that the systems of connect that the support points should resist. That implies directly into the sizing. And first you have the static loadings envelope with these loadings. It's important to say that they not occur concomitantly, but somewhen they can happen, and because of that, they are the ones that we should consider for sizing. And the dynamic loadings envelope that consider the seismic events, we have similarly the envelope that is generated that should be considered to the sizing process. About the adjustment requirements, we saw that before installing a panel, we should verify the structure we have to accept it or not, because the structure is not perfect. It has irregularities, and we should verify according to different verifications if we we can accept the structure and then install our panels or not. And with the limits given by the French document DTU 31.4, we looked for the worst cases, that is the case where the irregularities are in their limit of acceptance, and with that, with our on the dimensions, we could verify the length of adjustment that is required for the three directions, that varies from 10 to 30 millimeters, as we show in the image. Talking about the expansion gaps, we have the thermal variation, the temperature variation that varies also according to the region. Then here in the home, we have around 70 degrees of variation that we should consider. That generates, with our dimensions, around 4 millimeters of displacement in both directions, X and Z. Then, resuming, we have the strength that should be considered for the systems of connections in the horizontal plane. Here we have the global envelope. Then for the horizontal plane, we have values that vary from 2 to 5 kilonewtons that should be resisted by the system of connections, and higher values for the vertical reactions and the support points C and D that varies from 6 to 9 kilonewtons. About the adjustments, we have the lengths from 10 to 30 millimeters, as I said, that should be considered for all support points, because the irregularities don't choose one specific place to happen. They can occur in any place, anywhere. Then all the four support points should consider these adjustment requirements. And for these expansion gaps, we have two cases. Firstly, about the horizontal displacement that should be carried out by the left points, A and D, and we have the vertical displacement that should be carried out by the A and B support points. Then what do we propose? A solution, not necessarily, but solutions. That is a combination of brackets that are complementary between each other. And firstly, we have the type 1 with a horizontal plate that should be fixed to the structure, and a vertical plate that should be fixed to the facade. And if you get firstly the strictest case, that is the support point C, we can use the horizontal plate to fix the bracket to the structure using the oblong holes that we have to adjust the to the Y and to the X axis. And in the vertical plate, we can fix both also, because we are in the strictest case. Then always block it. We can fix in the all holes. If we look to the support point B, we should let displacement in the vertical axis. Then we should not use both holes of the vertical plate. We should use only the top one, because with that we can allow the displacement in the vertical plane, but not in the horizontal plane. In the inverse happens in the D point, where we should let the horizontal displacement, then only the bottom point of the bottom of the hole of the vertical plate should be used by a screw that will be fixed here. But it's different for the support point A. It's more complex. It should allow both displacements through the X and through the Z axis. And to do that, we do not propose two different holes, but one bigger that can allow both displacements. Then we can use again, the structure part of the bracket, that is the horizontal plate, to adjust through the Y and X axis during the installation, and the bigger hole to adjust the Z irregularities that we have, but with the enough space for displacing the facade in the uh, through the Z and through the X axis, that the facade will be moved while the bracket is fixed to the structure and is stopped. It's very important to verify that the head of the screw do not pass through the hole, because we need to block the Y direction of displacement. As we said, all the points should block the Y direction. And happily, we found easily document files that show it's common to have screws with a head diameter from twice to thrice the body's diameter of the screws. Then it seems to be applicable to our case. Then resuming our solutions, we have two types of brackets. Firstly, one that can allow only the Z or the X displacements, but also can block both. And we have the second type that mandatorily allows both displacements from in Z and X axis. We have also general properties with qualitative analysis that are described in the report, that are the ease of installation of the brackets, the universal usage considering for different materials of structures, the durability of the systems, and the disassemblability, that is the facility to accessing it to take off when it's needed without breaking the pieces, neither the facade. Then to conclude, what we have as perspectives for this study, if it's possible to be continued, we would like to have a real sizing of the systems, because we didn't size it, we just pre-draw after understanding the demands and knowing the right dimensions, the right thickness, the steel properties to the material of the bracket could be interesting. And as we said in the research, using as basis notably the Eurocodes, the fourth part of the second one that covers the connections for concrete structures, the first part of the third one that do similarly but for steel structures, and the first part of the 51 that covers all wooden structures. And with that, having parameters to size the brackets for all types of structures, all these three types of structures. Other thing can be the deepening of mechanical comparisons of the support points, that is adding support points or suppressing them, or even changing the initial conditions of them to verify how it implies in the reactions that are important about that are important point, as we mentioned about the mechanical functioning of the systems of connection. And we have finally the study of the financial impact, firstly of the system of connections to understand their real role in the panels, but also the participation of the wood frame facade budget in the general budget of a building. That, as I said, I felt the lack during the study of the information that is that is available in the academic world, and I think it could be very interesting to have more. I conclude this with the list of sources used thus far, and I thank you so much for your attention, and goodbye.